need a big chunk of the free space, a free hole. So finally we discuss about the paging approach. Paging is a fixed size of the data structure in the memory. So why don't we segment the logical memory, which means the program, and also the physical memory. Then as you can see, this one and this one, using the mapping table, memory management unit, we can page in and out. The page by page in and out, this paging approaches. So most of the nowadays the operating system use such a paging approach. That is the main part of the main memory management that we have discussed last class, and we are going to continue the chapter 9, which is the virtual memory. Okay. Do you remember one of the operation of the memory management is a swap operation? So what is a swap? It's not housewife's swap. So it's a very famous American reality show. It's not the wife swap, but it's a swapping one. In case we do not have enough space in the memory, just take out the existing memory, then bring the new process. So swap in, swap out, and swap in. Problem? You need I/O. A lot of I/O takes a long time. Practically, we do not use such a swap in and out. But you heard about the swap in and out many times in the computer science, or especially in the operating system. We will discuss how we can use such a swap, the mechanism of the swap in and out for the memory management. That is a virtual memory. Do you remember I showed a virtual memory of the Windows 10 or Windows 7.1? So even our operating system has a virtual memory. So what is a virtual memory? It's a memory, but it's a virtual. It's not realistic. The physical memory is fixed. We cannot increase the physical memory. If we can do that, wow, that's the perfect dynamically increase the physical memory. So please develop such a device, then you will be super rich. But anyway, it's a fixed size. We cannot. The operating system, any the algorithm that we have discussed that we are going to discuss operating system, due to the limitation of the resource. That's the problem. If we have the unlimited resource, so we don't have to worry about the many things. Probably the operating system textbook this much big. Okay. Because due to the limitation of such a physical, why don't we consider in terms of data structure, which means the page is the same thing. Okay, it's a paging data structure in the memory. It's the same data structure. However, it's not in the memory, but it's in the file system, hard disk. So if you take a look at the virtual memory setting on the Windows system, so you can actually change the size of the virtual memory. That doesn't mean that you can change the size of the physical memory. That means the specific area on your file system you can increase. Nowadays, Windows 10 supports dynamically increase the virtual the memory, virtual the space for the paging. But it's a rule of thumb. It's 2 or 3 times of the physical memory. Even though you allocate the 100 gigabyte of virtual memory, you cannot get the benefit of the virtual memory approach. So today we are going to discuss more about such a virtual memory. Okay. So we can define the virtual memory like this one. Separation of the user logical memory from the physical memory. What does it mean? User logical memory is a program. Okay? So the program from the physical memory. In other words, we will consider this is the physical memory, this is a memory map, this is the program, our program that need physical memory. So using the mapping table, like the page table, we can upload page by page. So we can upload the logical memory. So I think this is a logical memory. So
the physical memory. Okay, then problem is still for physical. No matter what the main memory management method you use, we cannot increase the size of the physical memory. So it's still limited. It's the same problem in the paging. So what if all the physical memory, the paging frames are used? There's no space at the time. So we can use the file system for the, in terms of data structure, it's a page by page. Okay? It's the same data structure, fixed size of it. Okay? However, it's reside on the hard disk drive, your file system. This is called the virtual memory. At the time, it's similar as a swap in and out. So in case we need a space, we can swap out and roll in, swap in. Similarly, this is called page out, and this is called page in. Okay? So because of that, there's such a number of pages or number of page out, number of page in are very good indicator to judge your performance of your system. Okay? So I have shown the VM state command. VM state command shows the such a page in and out, the statistics, how many of them are there. Somebody may be curious. Can we get the benefit of the performance when we are using the still hard disk drive file system? It needs the I/O input and output. So what is the benefit of using such a virtual memory? Can we get this something performance, the upgrade using this one?
Yes.
Yes, because file system, what is the file system? Later we will discuss. File system is a software. Software, you need something overhead, something addition, algorithm to read the data to maintain, manage the file. We will discuss later, okay, in chapter 10, 11, 12, something like that. So that needs overhead. That means it's a slower. So without using such a the file system, the function or overhead, we can directly access the hard disk drive, the raw device that structured by page. So we can reduce such an overhead to read and write the data. Okay, program, virtual logical program between the physical memory and this virtual memory. Because of that, even though you have the bigger size of the virtual memory, at certain time the performance will not be the increase, not linearly increases, but it helps so to reduce the overhead of using the file system. That is the idea of using virtual memory for the physical memory. Okay, so this is the solution. So we can use the virtual memory. Okay. Also, we can increase if we consider this area, the operating system consider this area as the memory, virtual memory and physical memory, but it's a memory structure, which means we can put more processes, which means it's a higher degree multiple programming. Okay? And also, what about the response time? Response time may be, okay, not always, but maybe the better. Okay, because it's the more program will be loaded. Later we will see the on-demanding, the fashion to execute the program, which means we are not going to upload the entire the logical memory to the physical memory, not all the pages in the program to the physical memory. We will select some of them, but there might be higher chances. So because we have the more the pages both in the physical and the virtual memory, so in terms of response time, it will be better. Okay, that is the benefit of using the virtual memory. So we will discuss, and also it can be implemented based on the demand paging on demand fashion. Okay. By the way, when it's 1999, I think I joined the IBM 2000 after the Y2K. I moved to the IBM, my hometown in IBM Korea. Then I realized that in the IBM, so everything is on demand. So at the time, it's almost 20 years ago. So they try to make the service, any IT service as the service, on demand service. So that was the reason why I was hired, because I was a database administrator. At that time, the IBM would like to make the new service for the database on demand. So, which means the customer doesn't have to install or purchase the Oracle database. Instead, through the network, IBM will charge it based on the number of queries or the number of usage of the CPU for Oracle database, something like that. And also, IBM definitely has the DB2, so we have the DB2 Informix and IBM, DB2 Informix and the Oracle, the database server. Customer can select any DBMS. So then it's paid by the usage. So I designed such a database as a service. Then nowadays I realized that whenever I met the IBM, the employee, they said everything nowadays is data analytics. So they focus on, they orient the data analytics in each and every area. Even one of my friends is elementary alumni. He worked for the IBM Austin to design the power chip. Then he moved to the TJ Watson, the White Plane. His job is optimizing the power when he designed the power chips, the CPU. That's critical. So otherwise, it's a lot of energy going out. It's hard. So optimization of the energy is very important. Then what he works for the department for the city of New York. Okay. Then he said it's the same idea, same mechanism, and same algorithm to optimize the energy, the power, utility line. It's like when you see the design of the chip, it's like the grid. Okay, it's the same as the CD structure, CD plan. So the optimization algorithm that he developed in the chip can be applied to the optimization of the energy utility, especially electricity grid. When they design the electricity grid, why do we need a grid? Even in the United States, if power out, you don't know what is the problem, because it's very, very complicated. So power is coming from here, and whenever new town or the zoning or the new residential area, they connect, it's messed up. Really. So still, do you know that after 9/11, 2002, there was a power outage in the Manhattan? Then the people close to George Washington Bridge very well because it's shut down everything. Still, we do not know what caused that problem. Because it's not the design, it's not optimized, it's not designed, it's connect whenever they need. So what he is doing is to design such a power grid and optimization. So then it's kind of analytics by analyzing usage of the power electricity. So here's the skill can be applied to the data analytics. Everything nowadays analytics, I think. So IBM is somebody say it's the kind of dinosaur of the IT company, but I believe based on my experience, they actually try to renovate every time and every, so to survive. That is actually the benefit of the IBM, even though it's old, the IT company, but they quickly change the decision. If this not going to be the benefit, they throw away. Like the IBM, the PC compete with Microsoft long time ago. It's OS2, but they throw away suddenly. Even though in terms of architecture, OS2 is much better than Windows, right? They throw away. Then the change, focus on the server. Then nowadays they throw away everything except the mainframe. Okay, that's the reason ThinkPad is sold to the China and everything. Then they believe the next decade will be data-driven, data something. So even though that will not be true, but maybe similar direction, because the IBM made the mega-sized company, IT company, think about that. So that's the things you can consider when you are looking for a job after graduation also. Okay, So that is the thing. We are going to discuss about the demand paging. So which means we are not going to page in all the pages in the program. Instead, only needed. Whenever we need, we will load the page in. That is the demand paging. Okay. So this is the same figure as, because I don't like that this is too simple, so I find this one from the internet. So it's cut right, but it's internally used. So then you can understand this is the program, and this is the main memory, and we can use the virtual memory space. Also, when we are using the pages, one of the benefit of the page is this is our process structure. So let's say we are going to divide like this, the page size. What about this area between the heap and stack? Usually in between, the blue part is not used yet. It's dynamically allocated, or even temporary space from time to time is occupied or flushed out. That this is dynamically increased when you are using the array and or other reference, but it will be free. We need to move all these pages into the memory. Is a waste of space. So when you are using the pages, even you don't have to the page in. Okay, you don't have to load this part, not used part, only needed part. You can load into the memory. Also, the data area is not the code, not data. Data can be changed, not frequently changed. It's a global value. But what about the code? It's not changed. It's the instruction. Also, it's the same as the process. Okay, if you are running the two Microsoft, the data part, the code part, the instruction part are the same. It's not changing. So another benefit of using such a page, we can, once we upload the page in, the code part, the instruction part, we can share. Of course, it's not changing. And also we don't have to load this part. That is the benefit of using the paging. Okay. So we can use such as shared pages for the shareable pages. Okay. So like the shared library, shared memory, and shared system library. So any shared part we can share. Okay. Also, this code area can be shared by the multiple processors. Even this part is not changed. It's the code part. Okay. So demand paging. So we don't have to load the entire process program into the memory. Only needed part will be loaded. So that is called the demand paging. In the extreme case, when you execute the program, you don't have to load any pages yet. Okay? First, main page will be loaded, only one page. So, operating system company, they try to put a lot of effort to speed up, to start their operating, the booting time, to decrease the booting time, shorter the booting time. How can they do that? What is the booting? So you need to upload the kernel, okay? Do we need to upload all the kernel?
No.
No. So only a few parts. So they try to optimize by considering demand paging. Also, after kernel is loaded, we need definitely service program, several programs, and they are needed to run other programs. So if the user encounter long response time, they fear that the operating system slow. So sometimes when they boot their system, some of the demanded page of the program will be loaded the memory. Then once the user execute the program, it's already loaded, so they can get the fast response time. So that is the benefit of the demand paging. Okay. However, we need to check which page is loaded, which page is not. Okay. At that time, do you remember how to protect the pages? In the page table, we can have the bit, valid, invalid bit. The valid means is in the physical memory page frame. The invalid is not. Okay, so same thing. So we can use such a valid, invalid bit to check whether page is loaded into the memory or not. So in cases not in memory, it's invalid. So we can bring them such a page into the memory. So this one shows the such an operation. So this is the not file. It's a file system, but it's for the virtual memory. So virtual memory, the main memory. So we can swap. It's the same operation as a swap in and out. That depending on the operating system, some of the operating systems still use the name of the swap, but it's a page by page, page in and out. Okay, so page in and page out. Okay, then so that the process that which is in charge of the such a page in and out is called the pager. Okay, ever used the pager? I know. So it was the 1992. So I got the first pager. It's the beeper. Okay, ever used? No, nobody. So I used the I got the pager from the old company. Then they provide me to call in case something happened from the operation room. So operator usually do not have any the authority to the act to do something in case something problem of the server. So they usually call me. But so because of pager, it's very easy to communicate. So really sick and tired to get such a call from the operation room. So midnight, like 2 a.m., 3 a.m., your job is to start and the database is not running. So I made the program using the Sun OS at the time. Anyway, what the operator is doing overnight is just checking the console, the log message. So I made the simple program to catch the log data if in case of Oracle shows the Oracle error code, okay, like the 0001, 0. Some of them are ignorable, but some of them are critical, like the 1555 is a snapshot to order. So we need to learn the query again. So I can catch using the graph. I make a simple shell script. Then finally, there's a command I'm not sure, so still use a tin. Tin was used to use the model. Okay, so using the model, put my pager with the message. It's a one line. It's a very simple and very good. So instead of getting the call from the operator, I can check the beeper, then whether this is critical or not. So but remote access at the time it was not possible. So because for the security there are two lines in the office at the time. One is for internet, another one is for intranet. So whenever I access the internet, I need to unplug the network cable and plug in. So because of the remote access was, but it's not that pager. Okay, so pager is in charge of such a swap in and out between the virtual memory and the main memory. Okay. So this is the page table with the valid and invalid bit. Valid means it was used for the protection. In this case, the valid means is in the memory resident. Okay. I means the invalid means it's not in the memory, so you need to the page in. Then if so we have the pages number as we have seen in the page table in your quiz in the morning. So once you decide this one is mapped to the page frame 3, but if this is invalid means it's not in the actually was in the physical frame number 3, but right now not. Okay, then at the time you can bring the page to not the page frame number 3. It can be different. In a plan, it can update. We will see the diagram how it works momentarily. Okay, so this is slide shows how it works. This is your program, logical memory, this is a virtual memory, and this is a physical memory, and then this is a page table. For example, the 0. A means it's let's say it's 1 byte page size. Okay, that makes sense. So this is a 0. 0 mapped to the 4. The 4 is here. It's a valid. Valid means it's in the memory. Right. What about the 1? I'd like the CPU write to access B. So 1. So 1 is, it may be something, the page frame number, but you need to check first to check whether it's valid or invalid. Invalid means it's not in the physical memory, but it's in the virtual memory. So then you can, it's a C. So 1 is a B is here, so you can load to the free frame, then the update, this one, like that. This is how it works when you access the pages. Okay. Then what if we cannot find the?
It's in main memory.
Sometimes there are two cases. In case of invalid, okay, invalid, we cannot find the pages from the page frame, the physical memory. So we need to bring the page in. Also, it's all occupied. So it's full of this user. It's full of the pages. So there's no the spaces at the time. We need to take out and bring the page in for the page. Both of them in IO. Okay, it takes time. So to handle such a cases is called a page fault. Okay, this is a page in. This is page fault. When you encounter such invalid, when you cannot find the pages from the page frame physical memory, that is called a page fault. So in case of page fault, we need to do something more. Okay, so at that time there's a page fault trap. So in terms of the interrupt, the operating system has a trap to check the design. In case page fault trap, so we need to solve then the find. First, you need to find the free frames. Okay. If not, you need to decide one of the frame as the victim frame. Then page out that the victim frame. Then bring the pages into the physical memory. It needs at least the two IOs, right? And additional operation. So this page fault causes the delay of the process, a delay of the system performance. So it's another very good indicator whether your operating system is a good performance or not. How many page fault last time, and who caused such a page fault? Okay, we will see some of the cases that cause the page fault later. So this is the very important characteristic. Sometimes depending on the operating system and the command, it's not the name of page fault. It can be different. Okay, some of them still use the swap, or as you have seen the previous CentOS. CentOS is swap pools, number of swap pool in and out. That is actually the same thing as the page fault trap. Okay, so today mainly we are going to see how to, the problem is, in case it's full of the pages, how to replace the pages. So the page replacement is one of the important algorithm and process to manage the physical memory. Okay, so this one shows the step by step in case of the page fault. What is the PBTR and the PTLR? Always we have the base address and limit address for the page table or any data structure in the memory. So starting and size. So the page table is a base register. Page table limit register. So using these two registers, we can find the location of the page table, then check the valid, invalid reference. In case of the invalid reference, it's a page fault. Then we need to find the empty frame. If not, so we need to decide one of the frame as the return frame, then swap page out and swap page in, and set the value as the read for the reference bit and start again. The next. So this is the page 4, and this slide shows such a step using the diagram. Then you can understand easily what's going on in case of the page 4. As you can see, at least we need 2 IO, page out, and page in, the 2 IOs to the memory. So, okay. For the demand paging, we don't have to load entire. Using the demand paging, we do not load the entire logical memory to the physical memory. Whenever we need, we are going to load, which means first time equals the page fault, because it's not in the physical memory. So whenever your program needs to access the instruction, it's not in the physical frame, it's the invalid. Invalid equals the page frame. So you cannot avoid, if you want to exceed the 100% the on demand, the fashion, first time is always the page fault. Then you need to page in such the pages. Okay. So this one shows the stages that we have discussed so far. So the step of the demand paging. Okay. So we can go over the step. Then we can calculate such a performance of the demand paging using the EAT, effective access time. It's not very complicated. Whenever many of the students consider, whenever they see the equation, it looks confused. No, it's very simple. The valid case and the invalid, and the valid case and invalid case. In the valid case, you can just consider the memory access only. No IO is required. But the invalid case, it's a page fault happen. Okay, so this is a percentile of the valid, and how many of times so it's a invalid page fault. How many of time? So it's a valid. It's a 90% or 10%, something like that. So it's 1 minus p plus p is 1, so it's a percentile. Then in case of the page fault, so we need to consider page fault overhead and the page in and out overhead. It's a time. So for example, so memory access time, the 200 nanosecond is 10 to nano is 10 to the minus 10 to the power of minus 9, right?
Yeah.
Micro?
6.
Right? Always I got confused. So it's 200 times the 10 to the power of minus 9, the second is a nanosecond, and the page fault service time is 8 millisecond, which means it's much longer than the memory access time. So at this time, if we consider the effective access time, it's the valid case, no fault. So this is the invalid case. The invalid case is we are going to consider page fault service time. So 8 millisecond is the if we consider the nano, the unit is 8 the million. So nano is minus 9.
Yeah. Yes.
K is
-3.
minus 3. Millisecond.
Milli is -3.
Minus 3,
Yeah.
and
Micro is
minus 6.
Nano is -9.
Okay, then there is a 200 times something like that. If we know the percentile, the ratio between the valid and invalid, so we can calculate such a effective access time, how much cost that wrong. So because of that, so number of page fault is very important to judge your system performance.
Professor.
Yes.
Can you go back to the previous slide?
Yes.
Yeah. What is the P? Yeah.
So P is the ratio, right? We have the invalid and valid case, right? The invalid means it's a page fault. And this one, you can read the page from the page frame. Like for example, 100%. So we can calculate 1 minus 0, 1, okay? And this is a 0, 9, 9, and this is a 0.1, something like that. It's a ratio between the page 4 and the normal, the access. Some of the operating system try to optimize such a demanded paging. One, so if we implement the extremely 100, not 100%, as much as possible on demand, which means there's no page in the memory, right? Which means the first page, definitely page 4. And second, maybe page 4, a lot of page 4 at the beginning. So, for example, the old BSD, the branch, the Unix, the BSD family Unix, they used such a, this one, oh yes, this one, the copy entire process, the logical program to the virtual memory only. Okay, not load into the page frame, the physical memory. Then, whenever they need, they bring page in. So, which means the beginning of the execution time, a lot of the page fault. Not a lot, but usually page fault. Okay, so to address that problem, some of the operating system, the load, okay, the group of the page at the beginning of the execution. Okay, so that is the way to optimize the demand paging. Okay, what about the mobile system like the Android and the iOS? They do not consider swap in and out. Okay, page in and out. Okay, so because still the page in and out need the I/O and overhead. Okay, other way to the people, the researcher of the operating system, they realize that many of the page fault happen when process is created. When you create the new process, definitely you need a memory space. Then need page in. Okay, is there any way to reduce the overhead? Think about the mechanism of the creating process. How to create the process using the fork and exec. What happens when you fork? Copy. Right? It's the same clone as the parent process. Okay? Then it will be separated by copying the children's the code instruction. Okay? Before that, it will be the same the process. Then from that idea, why don't we until the page is changed, when we create a new process, just share, because they are identical. We don't have to separate. Okay? If not changing, just share. So that is called a copy and write, like this one. When we create the process, if they are the same, just share the page from the physical memory. Until when? Until change it. If the page is dirty, the page is dirty means, first time when I hear the dirty buffer, dirty page, which means it's garbage. I thought that. So it's a long time ago. I actually missed it. The dirty means it's a change. It's a new one, actually. We need to keep 30 pages. So in case we have the 30 page, which means the page is updated or changed, at that time separate from the parent process. That's called the copy and write. The copy and write. So as much as possible, we share the page for better performance. Okay. Such a fork that use the copy and write is called a V-fork. Some of the students use the fork in their project 0, owning a project, but many of the students use the V-fork. V-fork is actually the utilize such a copy and write the mechanism when they create the process. Okay. The problem is, what if there is no free frame? As we discussed, we need to find the victim pages, the pages that should be the swap out. How can we decide? the victim pages.
We have different policies.
Different policy.
First in, first out.
Yes, always first in, first out. If old, maybe it's not used, okay? So we can take out. It's always fair? No. Any other idea?
LRU. They test used frame something.
Least recently used, right? LRU algorithm. As I think that in this class I mentioned the LRU is used for such a memory management a lot. Same thing here. So we can manage the list based on what? When it used. Least recently used. So it's based on. So LRU is the practically used a lot for the such a memory management. We will see such a the algorithm how to replace. That is called the memory, the replacement, page replacement. How to replace the page in case there is no free frame. Okay. So when do we need the page replacement? So this is a full, this is a physical memory, including 8 pages. So we have the DH and JAE, and we'd like to load M, this one. The 1 is not 0, 1. 1 is a 4. 4 is the valid, and this is M. Okay. Then the process. By the way, the page table is per process. Okay. Don't be confused. Except inverted. In case of the inverted management of the pages, is we have the frame, page frame, the page table for all the frames. Okay, then it has the process ID and it's the page number. Okay, so we have another process that would like to load the B, but B is not there, and there's no space. So at the time it's a page 4, and page 4 we need to find the free space, no free space, so we need to decide one of them as a victim. Okay, then load this one to that place. Okay, let's say this one is selected, so we can load into this one. That is called the page fault. Okay. This slide shows the mechanism of the page replacement. You can understand. So we are going to discuss about such a page replacement algorithm. For our practice, we are going to use the reference string. Reference string means it's a page number only. Okay? What is a page number? It's a program. In your program, we divide your program by the page size. Then number 0, 1, 2, 3. So 1, 2, 3, 4, 1, 2, 5 means from page, it's a program. Your program, the logical memory, that's number, so 5. You have 1, 2, 3, 4, 5 pages. Okay? Then this one is page C. And next, this one. Next, 3. Next, this one. And 1 again, 2 again, then 5, and 1, 2, and so on. This is just the string of the sequence of the page number that is needed on demand. Okay? And another example of such a page string is a little bit bigger. So who will test the performance of such a page replacement algorithm using these 2 page string? Okay. Our expectation is like that. The more page frames, which means the bigger size of memory we have, the better performance. Why? This is the number of the page fault. The last page fault is better. Is it true? Yes, that's usually what we expect. Not always. Sometimes, even though we have the bigger, more the page frame, but page fault is increased. We will see why. Okay? So that is sometimes happen. So first one, as I've mentioned is a first in, first out. How can we decide the victim? Old one will be victim. So let's start from the. This is our page string. Okay, so we need 1, 2, 3, 4. Some of the students confused what is the array of this one. This is a time by time. Okay, this is kind of time along the time. So this is our memory. How many page frame we have in the memory? 3. Only 3. Not 3 by this one. Some of the students consider it's kind of 2 dimensional array of the memory. Doesn't make sense. So this is a time. Okay, this time. So when we use my own the page frame, it's my memory. Okay. So first I need the 1. Is there any 1 here? No. So 1 will be the page in. How many page faults so far? 1. Because it's a page fault, you cannot find it. I'm not going to manage the page table. If you need to manage the page table, 0, 1, 2, 3, 4, 5. In this case, 1, 2, 3, 4, 5. And page frame number. And valid, invalid. You need to manage. So definitely 1 is nothing. It's an invalid. So it's a page fault. Next, 2. There's no 2, so page fault is 2. Next, 3. Page fault, so 3. So up to this time. What about 4? Is there any 4? No. So we do not have the, we cannot find the 4, and also we do not have the free frame. So we need to decide the victim this time. Okay? How can we decide? First in, first out. Which one is the oldest one? Take a look back. This one is the oldest one. So this one will be replaced. It's a page 4. The next one, 1. Do we have 1 here? No. So this one is the oldest one. So this one will be replaced. So page 4 to so far 5. And next one is a 2. Unfortunately, we do not have 2. So page 4 is a 6. And next one is a 5. Which one is the oldest one among this? 4. So 5. So 7. The next string is 1. We have it here. So it's a page in. No. So you don't have to page in. So you can just read the data from this page frame. Okay, no page 4. The next one, 2. 2 is here, no page 4. And next one is a 3. 3 we do not have. So which one should be replaced?
1.
So take a look back. Which one is the oldest one among 5, 1, 2? 1. 5 is the oldest one. Right? Just our rule is first in. It doesn't matter whether it's used or not. Accessed or not. Just the first in arrival time is our criteria. So 5 will be replaced by the
1 will be replaced. 1 will be over.
Oh, this one is oldest one. Sorry. So 5 and this is the 3.
But 1 has been recently utilized. So
That is the recently used, different address. So this time we will consider only the first in. Okay? What's the difference? If he suggested this one is recently used, so maybe higher chance to be reused. Okay? That's true. Problem? Hard to manage. Okay? This recently used data should be managed separately. So it's allow the overhead. First thing, you can just take a look at linearly, then get it this one. So that's the benefit, that's the difference. So the page 4 is 8, then 3, the 4, this one, 2 is here, so 4, then 5 is here. So total page 4 is 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is the first in, first out using the this first reference string. What about the full frames case? Okay, fourth frame. I'm going to explain the using this one. Don't be confused. This is not the two-dimensional array of the memory. It's just along the time. So 1, 2, 3, 4. Be careful. All of these are page fault because on demand paging, the usual beginning of the page on demand is called the page fault because they are not in the memory. Then 1, 2 we used. Okay, and 5 is not there, so 1 will be replaced because it's the oldest one. Then the 1 in case of 1, so no 1, so 2 is the oldest one, and 2, 3. So 3 will be replaced, and that goes the page 4 to page 4 to page 4, and the 3 will be replaced by the 4. 3 replaced the 4, that's the oldest one, and in case of 4, 5 is the oldest one, and in case of 5, and the 1 is oldest. How many page 4? 7, 8, 9, 10 page 4. Is it normal or a little bit weird?
Weird.
Because when we see the number of frames by the page 4, we expect a better performance. The more page frame we have, the better performance, the less page 4. However, in this case, the more page frame we have, the more the page 4. This is called the Pilates anomaly. It's an anomaly situation, not usual situation that, however, that may happen. Why this one is happening? Because of the pattern of the page string. That usually happen in real life system. Real life system, not the think about the programming. Sometimes it's a routine, a lot of routine, or the library or object will be called again and again. Some cases like this one, you can see the 1, 2, 3, 4, and 1, 2, 5, 1, 2. So it's the previous one, last one is called again, again, again. Okay, kind of routine. So at the time, it may cause such a more page fault, even though we have the more frame. That is a Pilates anomaly. How can you address such an anomaly?
Changing algorithm.
We can change the algorithm by how? We can later we can consider locality. Locality means, for example, 1 to 3, 1 to 3, in this case 1 to 5, 1 to 3, some we can group some of the pattern of the pages. Okay, that belongs to the same routine, same function, or same object. Okay, so if we can consider such a group of the pages, which means a locality, and we can reduce or avoid such a Pilates anomaly. Okay, so that is you can do by yourself. In long case, okay, practice. Who knows? I have another pop-up quiz next class. Okay, so why don't you test whether 3 frame and the 4 frames it has the Pilates anomaly or not. Obviously, this is a good example of the mid-final exam. Okay. Okay, so this slide shows the Pilates anomaly using the same graph, the number of frames versus this one. Why we have this one? Because of the pattern of accessing the pages or routine. So how can we address? By considering the locality. Later we will see how the real operating system find the locality. It's not easy to find the locality. Okay, each and every program has a different such a pattern. Next one, I think that we can do more. 5 minutes is enough to discuss the algorithm. So next one is the optimal algorithm. Optimal algorithm. What is the ideal case to when we replace?
So page
If the page, so this time, so 1, 2, 3, 4 is a page fault. We cannot avoid this page fault. At this time, 1, okay, no page fault, 2, no page fault, but this time, 5. So 1, 2, 3 for those, no 5, we need to decide the midterm. The first thing first up, we take out the 1 page out because it's the oldest one. Right? Who knows? 1 can be reused. Right? the next time, like that caused the ladies anomaly. So we will take a look at the next string. Whether one is used one is the next one. So we are not going to replace. What about 2? 2 will not be replaced because it will be used soon. 3, yes. But 5 is the last one. It will not be used soon. Okay? We are going to select the page that will not be used soon. Okay? Then 4 can be replaced. 4 is the last used in the future. Okay? Then 1, 2, 3, then the 4. This time it's the end of the string, but if you have the more string, take a look at whether 4 will be used, or the 2 will be used, 3 will be used, and 5 will be used. Okay? No, it's 1. This time 1, 2, 3, 5, take a look at the future and replace it. So that is called the optimal algorithm. Very easy to see the future than the replace. Not used, not recent, not will be used recently. Okay, that is the optimal algorithm. Then we can avoid the problem of the delays. Problem is the best case, best algorithm. Processing.
Analyzing.
It's not possible. Can you see the future?
How can we see the
Yeah, how can we see the future? So it's not realistic. So this is the reference algorithm, ideal case. Okay, if you have the new algorithm for the replacement, then compare with the optimal algorithm, then you can achieve. Also, there is another way to, we cannot see the future, but we can estimate. Okay, we can predict using what? Frequency or journal data, log data, history data. Using the history data, which page will be used soon, which page will not be used soon, we can predict. And using the Bayesian algorithm or some Kalman filtering or heat Markov model. These are the algorithm to predict the sequence of the data along the time. Okay, so you probably heard about the Markov chain, or hidden Markov model, or the Kalman filtering, or extended Kalman filtering. In terms of statistics, the regression model and the Bayesian approach, these are the prediction model. Based on the history, based on the, if we have the 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, in future it will be 1, 2, 3, 4. It may be. So that's the idea of the prediction. So some of the operating system use, but not always, use such a prediction model to optimize such an algorithm. So you can practice such an optimal algorithm using the reference string. Then, for realistic, as some of the students mentioned, why don't we can see the past, right? We have its history. If the reference is used recently, maybe higher chance to be reused, right? Because it's a frequently accessed. So at that time, instead of the arrival time or the in time, we will consider when is the last used. Then we try to keep the recently used one, and also we try to decide the victim page least recently used one. Okay. So for example, up to this point, so it's automatically page 4 because we do not have anything. Then 1, 2 is okay. In the 5, okay, 1, 2, 3, 4. Among them, the 1 is used here. 1 is used here. 2 is used here, and 4 is used here. 3 is the least recently used one. So instead of 1, we will decide the 3 as a victim. Okay. Then apply the same algorithm. 1, 2, 3, 4, 5, 6, 7, 8. So page 4 better than first in, first out. Equal or better than first in and first out. But not better than the optimal. Optimal is ideal case. Okay. So this is the value algorithm. Problem? I already mentioned. It's hard to maintain the history. For each page, we need to manage the history when it is used. In case of the first in, first out, it's not changing. We can just take a look back. Right? In case of list listen to use, each page maybe change it. We need to maintain, manage the history of that. So track time is very hard. So there are different ways how to manage the list listen to use time. Any idea? Homework. Think about it. You don't have to submit anything. I'm going to ask in the next class. Okay, so that's it. Any question?